I wanted to start okay, good afternoon. So, unfortunately, I don't know for some reason again this projector is not working. So, okay, and then I think you have already seen that I have announced an extra lecture for you tomorrow. And now they actually told me that that room is not available. I am not sure if E31 has a camera. I don't know. I will contact them. So hopefully you will be there. Yeah, I will let you know about the room actually for tomorrow. But I want to start a little bit conceptual lesson today from the beginning to the end. I know that we talked about integration by parts, and we are supposed to go for examples, and I also need to teach you how to do to learn method of partial fractions. But if you don't mind, for this lesson, let us concentrate on this more conceptual one, and I will take care of that tomorrow. So that's more technical, so it's an algorithmic bit, but this is a little bit more conceptual lesson. So let me, it's very hard for me also not to see what I'm going to do. Okay, so I need these probably pens. Okay, so do you remember we talked about finding antiderivatives? And yesterday I told you just consider this as a mathematical curiosity or just a game. So that if I give you a function, then I ask you, can you give me a function whose derivative is this function, which is called a primitive function or antiderivative. But I didn't tell you why people are getting interested even to do this game. So it might be today we will be able to at least answer that part of the question. So we want to talk about definite integrals. So in this topic, what we want to talk about is the concept of lower sum and upper sum. Of course, we can say Riemann lower sum, upper sum, and then finally Riemann sum. Okay. But there are a lot of terminologies that I have to introduce, but everything is very simple. So, I hope that I can cover it in a nice way today. So the first thing that you need to know is the notion of a bounded function. You already know what a bounded function is. And in this actual topic, I always work with closed intervals from A to B. So a function is bounded if it means that it will not actually pass some threshold from above, it does not pass some threshold from below. That's called a bounded function, yes? For example, the very famous bounded function is sine function. It cannot go beyond 1, it cannot go below -1. But for example, if I just tell you what about the function f of x equals to x squared, of course this function is bounded below because it cannot go below 0. But it is not bounded above because it can be extremely large by making it very large. But even if this function is limited to some kind of interval, let us say 1, 2, 3, then this function is still bounded if I limit myself within this interval. Yes. For example, if I want to draw this, so if it is 1, here it is 1. If it is 3, of course this will be 9. Then you will see that I have this scenario. So even though the whole function, if I just say this function is bounded, of course the answer is not. It's bounded below because the numbers are non-negative, but it cannot be bounded above. But if I limit myself to a very limited interval on x, then of course this function is bounded. Okay? But one thing that is important, I want you to differentiate. This is not it's not part of your course, but I think the topic is so simple. Let me just tell it, because if you want to do the integration theory properly, you have to know the notion of infimum and supremum somehow. Okay, so these are big names for a very simple thing. Okay, so in this function, This function is continuous on this closed interval. The max-min theorem guarantees that there is a maximum and there is a minimum. So here, if I ask you what is the maximum of this function on this interval, the maximum is 9, and it is attained when x is 3. Minimum is 1. It is attained when x is 1. Yes? But now, let me change my interval to another interval, for example, here. If I make it, for example, to 3 and then open it. So it means that I want to make this one single point hollow, okay? In the previous case, if I ask you what is max of f, you would say it was 9. If I ask you what is mean of f, you would say it is 1. But now, what happens here? If I ask you what is if I have this function, but I have this interval, what do you say about max and mean? So what is mean of f?
It's still 1.
It's still 1. And if I ask you what is max of f,
We need to do them.
it does not exist, yes? Max f does not exist. This is important to understand. When you say maximum, maximum and minimum means it should be attained for some value. So for these functions that we don't have the concept of maximum, there is something called supremum. It means that our supremum of this function is still 9. Supremum of this function on the interval from 1 to 3 is still 9. Okay? So what does it mean? It means that this is the smallest upper threshold. So it is not a maximum, okay? But 9 is the smallest upper threshold. Because if I go below 9, if I, for example, stay here, then there are many points on the graph which are higher than this one. So this 9 is on the one hand the upper threshold because all the graph lies below it, but it is the smallest upper threshold because even if I come a little bit lower, then there will be a lot of points will be higher than that one. So that is the concept of supremum. And the other way around for minimum, if I take this off, and I talked about if I take this off, and now suddenly the minimum will not exist again, but then I can talk about what is called infimum. Infimum, so supremum and infimum. So infimum of the function f on this, so let me now make it this one, on this interval. Can you answer the question now intuitively? It is still 1. Okay, so this is important to recognize between these, but for your course actually, if maximum and supremums are the same, if this is a closed bounded, yes, if I for example fill it back, if I ask you what is the maximum, you will tell me it is 9. If I ask you what is supremum, it is still 9. So if the maximum is attained, it is automatically the supremum as well. Okay, is that clear? It's a very simple topic. Any questions? Okay. This is something about bounded function, and this is something about supremum and infimum. For your course, most of the time you can consider supremum as the max and infimum as the mean. The only difference is that supremum and infimum are not necessarily attained. That's it. And the other thing that you need to know is the notion of a partition. So, what is a partition? So here, now what I have always a closed interval, and I can talk about a partition of a closed interval. What do I mean by that? It is a set that starts, so it is a set like x0, x1, x2, up to x sub n minus 1 and xn. When I talk about a partition of a closed interval, I mean a set of this type, so that the first element is a itself, but these elements are in increasing order, strictly increasing order, so it means that x0 is strictly less than x1, x1 is strictly less than x2, and it continues until x sub n minus 1 for some particular n, and it is strictly less than the last one, but the last one by definition is B itself. That's the meaning of a partition. So it's a bunch of numbers between those two limits. Okay, so for example, if I give you the interval to be 1 and 5, I can have different partitions here. Yes. So for example, if I draw this line for you, so here is 1, for example, here is 5. So for example, I can have this partition, let me call it partition 1. I have to start with 1. I have to end with 5, but that is up to me. Any finitely many numbers between 1 and 5, I can arrange them in a strictly increasing order here. For example, I can decide to write it as 1, 2, 3, 4, and 5. Okay? So if I look at this partition, so this is 1, 2, 3, so it's 4, and let me bring this a little bit closer. 5. So this is a partition of this interval. So in this partition, I have also sub-intervals. How many sub-intervals you see? This is why it is called partition. These numbers partition this one single interval to some sub-intervals. This is the first sub-interval, this is the second, this is the third, and this is the fourth. Okay? And then of course I can have a different partition. For example, I can have P2, it has to start with 1 definitely, it should end with 5. I don't know, for example, I can decide put 3.5 here and 4 here. That's also another partition. So the concept of partition is actually extremely simple. Every point inside my partition is called a node. These are just terminologies, we want to use them later. And the number of partitions, so here I have 1, 2, 3, 4 partitions. Here I have 1, 2, and 3 partitions. Yes. Another thing that now my question is that in the general case that I have n, so what is n here? This is the 0th term, 1, 2, 3, 4. So in this problem, n is 4. In this problem, this is the 0th term because by convention in your book we start from 0. So this is the 0, this is 1, 2, 3. Yes? So what do I have? I have n equals to 3. So my question for you is now that if I have a general partition with n plus 1 nodes of this interval, can you tell me what is the kth interval? The kth subinterval. Yes? So how should I write that? So you see, from 1 and 2, it is the first interval. So let me write it like this. From x0 to x1 is the first interval. From x1 to x2 is the second interval. From x2 to x3 is the third interval. So the kth interval will be from where to where? When you say first interval, the right index is 1. When you say the second interval, the right index is 2. So when you say the kth interval, the right index will be k, and the previous will be x sub k minus 1. So it's good to know. Okay? And then there is another concept that you can say that what is the length of the kth interval? The length of the kth interval is denoted by delta x, and then you equip it with an index k. So this means the length of the kth interval, which is extremely simple. What is that? It is x sub k minus x sub k minus 1. Okay, one more thing. This is the kth interval. If I ask you what is the next interval, what do you say? What is the next interval? Interval number k plus 1. What is that? It starts from xk and it goes to xk plus 1. So something I want you to know, this xk is a member of the kth interval. It is also a member of the next interval because the intervals that I am considering are all closed. Okay? And this is the length of the kth interval. So now can you tell me, so this is something that we needed. And one more thing is that you see that this partition, if you prefer to it is up to you. Which partition do you prefer to work with? This partition of this interval or this partition of that interval? Yes?
The first one.
The first one, because it is very regular. Yes, I have the same length as everywhere, so I can work with it easily. So there are some nice patterns that we can actually work with. This is called a regular partition. It's called a regular partition. So a regular partition is a partition that the length of each subinterval is the same. Yes? And can you tell me what will be if I have a regular partition, do you agree that in a regular partition what I can write? I can write delta x1 equals to delta x2 equals to up to delta xn. All the lengths will be the same. And it will be equal to what? Can you tell me? It's a partition of the closed interval from A to B. There is no guarantee that the partitions have the same length. But if all of them have the same length, then it is called a regular partition. Then I can write a formula for the length of each one of them. And that is equal to the total length divided by the number of intervals. So what is the total length from A to B? The total length is B minus A, and I divide it into n equal pieces. Yes? And one more thing about partitions is two more things. One thing is called the norm of a partition, norm or mesh. These two words we use for a partition. And we denote it by this symbol, norm of my partition. It is the longest length of the subintervals. That's called the norm. So for example, can you tell me what is the norm of this partition? The length here is 1, 1, 1, 1. So the largest one is also 1. So the norm or the mesh of this is 1. And can you tell me what is the norm or mesh here? This length is 2.5. This length is 0.5. This length is 1. So what is the norm? 1.5. 2.5. That's the mesh, or that's the norm. So for a regular partition, the mesh or the norm is equal to the length of each subintervals. One more thing about regular intervals. Can you tell me, is there any way that I can write a formula for node number k? So for example here, you see if I ask you, this is the first node, second node, third node. So if I want to reach to 4, I start from 1 and I add 3 length of subintervals. If I want to reach to this, I have to add 4 length of subintervals to 1 to reach to 5. So if I want to reach to x, the node number k, I start from node 0, which is A by definition, and then how many intervals I add to it? K intervals I add, but because this is only for regular partitions, this is B minus A over N, only for regular partitions. Okay? Is that understandable? Okay. So now I want to go back and talk about this. Let us concentrate on the lower sum. Okay, so now the real lesson starts from here. So I give you a function. I give you a closed interval. I give you a partition. Not necessarily regular, any partition. Okay, the only thing that I ask is that f is bounded on A and P. So I'm not even talking about f is continuous. F can be continuous or discontinuous, but it is bounded. Okay? Now I want to introduce the notion of the lower sum or the Riemann lower sum. Okay? This is denoted by L for lower and I for function and this partition. So the lower sum is a number, as I will define shortly, which depends on your function and on the partition of your interval. How is it defined? It is defined in this way. You write m1 delta x1 plus m2 delta x2 and then continue until mn delta xn. You don't have any problems with these notations. Delta x1 means the length of the first interval, delta x2 means the length of the second interval, and delta xn is the length of the last interval. So I have to tell you what do I mean by these little m's. These little m's, let us take one of them. Let us say little m number k. Little m number k is the infimum of your function on the kth interval. This is the kth interval. So that's the kth interval. I denote it like this, okay? So you might say why we are interested in this. I will motivate you about that. But writing the lower sum is an extremely easy task. A function which is bounded on a closed interval is given, a partition is also given, then you're supposed to find this number. This number is defined in this way. Delta x's are the length of corresponding subintervals, and these m's are infimums. For your course, most of the time, instead of infimum, say minimum. There's no difference, but the correct one is the infimum. Okay, but before going to the upper sum, let us understand what is the meaning of this number, what we are actually calculating. So for this one, let me give you an example. So let me give you the function to be x squared. Okay, and let me, I don't know, for example, give the interval from 1 to 5. And let me also give you a partition. Let us not choose it regular for the first time. So I would write 1, 2, 3, and jump to 5. That's a partition for this function on this closed interval. Now I'm asking you, let us calculate that lower sum. So I want to calculate the lower sum of this function for this given partition. This is my question mark. Okay? Okay, let me draw a picture for you that's easier to understand. So I want to draw it somewhere that we can keep it for a while. So let me just draw this here. So the graph of fx equals to x squared is simple. So I don't need the negative side. So it means I'm not caring about that part. So let us exaggerate a little bit. So let us assume that this is my function f of x equals to x squared. And then I am from 1 to 5, so let us concentrate that here is 1, 1, and then 2, and then 3, and then 4, and then 5. So I'm here. So 1, 2, 3, and 5. That's my partition. Yes? Okay, and now what I want you to do is to write the formula. So how many intervals I have here? How many subintervals I have? 1 from 1 to 5 in this partition. 1, 2, and 3. So this means that I have to calculate M1, I have to calculate M2, I have to calculate M3, and I also have to calculate delta x1, delta x2, and delta x3. Yes, why? Because the formula for this case is just simply M1 delta x1, M2 delta x2, and M3 delta x3. Do you agree? Okay, these are very simple. Let us do the simple ones first. What is delta x1? Is the length of the first subinterval, which is 2 minus 1, which is 1. Delta x2, the length of the second interval, which is 3 minus 2, which is also 1. And delta x3 is what? Okay. Just for your understanding, what is the mesh here? The mesh of this partition is the largest one too. But now let us understand M1. M1 is what? Is the infimum, but in this case, because the function is continuous, completely forget about the word infimum and think about minimum, because they are the same. Okay? I want to find the minimum of my function. When I say minimum, I mean the minimum value. I mean the y coordinate. of the function on the first interval. So let me just try to draw some pictures here for you. So for example, concentrate on this subinterval, and now I ask you, what is the minimum of this function if I am limited between 1 and 1? So what is the 1 and 2? What is the minimum? The minimum is this height. Do you agree?
Yeah.
This is the minimum. And if I ask you what is this height, how should I know? This number is 1. This function is x squared. I feed it into the function and I get the height. The height is 1. So very simple. M1 is 1. Okay? Now I go to the second interval. So this was the first interval. I go to the second interval. Yes? And now I want to limit myself here and I ask you the same question. Can you tell me what is the minimum of my function on this interval? It is this length. Do you agree? So this will be, so in this picture, this is M1, this is M2. But what is the value of M2? Is the height, is the length of that green line, which is 1. So this is 1 to power 2, 1. This is 2 to power 2, 4. That's M. And let us do the next one. So this is the third interval now. The third interval is a little bit longer. But do you see that what is the minimum again?
3.
The minimum is happening at 3, but I want the height. The minimum means the height. So what is the minimum here?
9.
3 to power 2, 9. Okay? And now what I am doing is that multiplying these case by case, so I found the answer. So LF of P is equal to this number, M1 times delta X1, plus 4 times 1, plus 9 times 2. So what's the answer? 4, 5, 23. That's the lower sum. But let us understand what we have done geometrically. So can you tell me what is the interpretation of M1 delta X1? Delta X1 is this length, M1 is this length. Do you agree? When I multiply this, it means that I am finding the area of this rectangle. Yes? Do you agree? Because this height is 1, this length is also 1. Of course, this is not a rectangle, this is really a square. I have rescaled that. Okay, but I am finding the area of this. Do you agree? And now let us see what I am doing next. 4 times 1. What is 4 times 1? 4 is this height. 1 is this length. When I multiply that, what I'm doing, I am finding the area of this rectangle. And then when I multiply 9 by 2, what I'm doing, so let me go a little bit here. So this is, let us keep it. And then 9 times 2. 2 is this length, 9 is this length. So if I multiply them, I am calculating this area. And if I ask you what is this lower sum, is the sum of all these rectangular areas. Yes, do you agree? So this is what we have calculated geometrically, so if you want to get a feeling about it. And of course, one thing is clear. If you limit yourself on this part of the curve, yes, if you limit yourself here, then there is an area below this curve and then above the x-axis, which is between this line and that line. Okay? So it is very clear that this number is less than the area that I described now. Yes, I will call that area A. So if I ask you what A is the area here. And it is very clear that this sum is definitely smaller than that area. Is that clear? Okay. But now immediately let me jump to the upper sum and let us see what happens. Upper sum is denoted by this U, F of P, U for upper. It is exactly the same, but instead of little m's, I will have capital M's. And capital M's are supremum, or the maximum, instead of minimum. So for example, in this case, it is capital M1 delta X1 plus capital M2 delta X2 plus capital M3 delta X3. Yes? Okay. Now, can you tell me, so the deltas are the same? So I need to calculate M1, M2, and M3. Can you do it for me? Now look, I go to the first interval, but instead of picking the infimum or minimum, I this time pick maximum. Okay, so can you tell me what is M1? I am on this interval, but the highest value is this,
4.
is 4. Yes, so it is 2 to power 2, which is 4. And I go to the next one. I pick the highest one. What is that?
9.
The highest one is 9. And then if I go to the third one, the highest is
25.
5 to power 2, 25. Yes? And then if I want to calculate this, I will multiply 4 by 1 plus 9 by 1 plus 25 by 2. So it becomes 5963. Is that right? But now let us understand what we have done here. Let me change my color. So let us draw something. What is that? What is the geometrical interpretation of the first number? 4 times 1. It means I am on the first interval. This is 1, this is 4. When I multiply them, actually I am making this rectangle. Yes? And if I go to the next one, M2 is 9, which is this height, multiplied by the length of the second interval. So this means that I am constructing this rectangle. The second term is the area that you see here. And finally, the last one, hopefully you can see, will be the area here. So this is the total area. Yes? Yes?
How would this look like if it wasn't such a nice, constantly increasing function?
It doesn't matter. It will be more complicated. It doesn't matter. Might be the maximum or minimum are not occurring in the end points. It will be in the middle points. But for example, if that is the case, and this is the highest point, then you have to construct a triangle like this. And if this is your minimum, you just go below it. So it doesn't matter. You find the max and complete the square. You find the min and complete the square or the rectangle. So this 63 is the sum of these orange rectangles. Okay? So one thing is very clear. That area that I talked about it for you is sandwiched between these two numbers. Yes? So it's very obvious that this A, the area below the curve, is definitely larger than F lower sum. Yes? And it is also definitely lower than the upper sum.
You can't simply take the average, right?
No. Because it is very more complicated than that. This function might be nice and it even more might be coincidentally works, but there is no guarantee that this is going to work. But this, I'm not taking some things for granted. But this is more or less obvious. Yes. But now one more thing that I want you to understand is that what happens if I start increasing the number of points? So that's the whole point. Because I don't want to make things very hard, let me just add one more point. And for example, this one, let me define for you a Q. But Q, let us make it regular. 1, 2, 3, 4, and 5. Yes? So let us see what happens. So this means that now my points are 1, 2, 3, and now I have also 4 and then 5. Okay? Then, do you expect that this L and F U will change if I change P to Q?
Yeah.
Yes. But let us see how it will change intuitively. Okay? So, do you agree that the first term will remain intact because nothing has changed there? The second one will be remained intact, both for L, both for U. But this one will change because then I will have another line that I have to consider. So, then I will have, for example, let us concentrate on the green ones, which are the lower sums. The green one will now become a blue one here, because there is nothing changed there. This green one also becomes a blue one here. Nothing has changed here. But this one will change. So can you tell me how it will change? On this one, I have this length multiplied by my minimum. The minimum is this much. So if I complete that rectangle, it will be this. Yes? So then I get this blue rectangle here.
the minimum is increasing and the maximum is decreasing.
Yes. And then if I go to the next one, this is the length, but this will be my minimum. And if I complete that, it becomes this rectangle.
And it gets closer to the area.
Yeah. So it means what is happening, the error that I am making for that area becomes less, because before this blue area, before these blue areas, the error that I was making was this much. But now that I am adding 1 point to it, the error that I am making for that area is this much plus that much, which is lower than the previous error that I made. So it means, but still you agree with me, the sum of these blue ones is still below, okay? But it is still, so A is still below, A is still larger than the lower sum, but the new lower sum, it has increased, yes? F and Q. But if you draw the picture again, I don't want to mess it up, you can convince yourself that the upper sum will get smaller this time. So that's the whole point. So this means that by adding more and more points, I will make the upper sums smaller and smaller and getting closer to the area from above, and I am making the lower sums bigger and bigger and making them closer to the area from below. Is that right? Now, if you are a mathematician and you really want to define the area, what do you think the area? What is the main property of this area? Can you understand something from this, what I described here for you?
Area under the curve.
So what is that area? This is a number. Area is a number. But what is the property of that number? Whatever this area is, it is always less than
the upper.
all upper sums, and it is always greater than all lower sums. This is intuitively clear. And this is the base of definition of definite integral. We say that A is the definite integral of the function f over the interval from a to b. So we denote it by this symbol. So if so this area, in this case, it is clear that this number is one unique number which lies below every upper sum, simultaneously above all lower sum. This is the motivation of defining the integral of a function. Okay, this number is denoted by the integral. This integral, by the way, is s, because you see it has something to do with sums. So this is the integral of my function from a to b. Is that clear? Yes or no? Okay, so now if I want to tell you what area is, I would say area is that number which is uniquely determined and it is smaller than all upper sums and greater than all lower sums. So that is the motivation of defining the integral. Yes, please.
Why is there the less than equal to sign? Because when would it ever be equal?
Pardon?
In the inequality there, it says area is less than or equal to upper sum,
Mhm.
or greater than equal to lower sum.
Yeah.
When is the case that it's equal?
For example, if the function is constant.
So like a straight line.
Yeah,
Okay.
it can happen. So that's why if I write this strictly, by the way, strictly is probably wrong, because if I want a number which is strictly than everyone, there will be more than one. So it cannot be unique.
Okay.
So but it can happen that if you have a straight line, this would happen.
Okay, thank you.
Yes. Okay, so now this is the motivation. Any questions? Okay, this is the motivation what we are doing. But let me immediately solve one exam problem. So related to these Riemann sums, let me describe it. It's very hard that you don't have access to it. Of course, if you go to lecture notes, I have already done that. So please, at least you can open it up and see how it goes. So this is exam question from 2020. So let me describe what is it talking about. So here, let me describe what it means. So a function is given to you. It is 3x. They have intentionally made a simple function, and they have given you a closed interval which is from 2 to 3. And then they say that and p sub n is the regular partition of this interval into n equal pieces, equal subintervals. They are just telling you this in the exam. Of course, each of length 1 over n. Why? Because the total length is 1, and then if you chop it into n pieces, equal pieces, each piece will be 1 over n. All this information is given in the problem. And they have told that let L, Pn be the lower sum. So the notation is slightly different from me because they have already introduced you the function, so they don't need to name it again. So that's why they are saying that this is the lower sum. Okay, the question is that find a formula for this and then calculate what happens if you calculate this limit and send n to infinity. Yes? Why infinity is a good choice? Because hopefully you can see if I want to get closer and closer to a, I have to divide this into more and more pieces. When I divide it to more and more pieces, it means that the number of points that I am bringing in is going to higher values. So intuitively, it seems that if the number of points is infinitely large, I reach to this number that I am looking for. So that's why this limit is good. Yes?
Is that only true for regular partitions? Because
It is true for what?
for regular partitions, because you could fit infinitely many points between 1 and 2, for instance, and leave the others empty.
Yes, you are right.
Okay.
So this is not true. This is for every partition, not just regular. So it doesn't matter if you add points to your partitions, you are making the upper sums smaller. In this case, this is. Are you talking about this scenario or this one?
That scenario.
Yes, that scenario they have mentioned it is regular. Okay. Okay, so I want to calculate this LPN. So how should I do that? So let us draw a little bit of pictures here. So what I have here, it is a line, 3x from 2 to 3. Okay, so I don't know. For example, let me consider here is 2. Let me consider here is 3 to a little bit exaggerate. When I give 2 to my function, it becomes 6. When I give 3 to my function, it becomes 9. So these are the points that I have. And what type of function you are facing? Everyone knows that this is a straight line. So this is the function that I am looking for. So this is my function, f of x equals to 3x. And they are asking me to find L for that regular partition with n nodes for this interval. So what is we write the formula. So what was the formula, do you remember? It was little m multiplied by the corresponding length. But here, because I am working with n of them, either I have to write n of them or use the sigma notation. So I would write it as sigma m sub k multiplied by delta xk, and I run k from 1 to n. I want to calculate this. Yes? In this problem, delta xk is very simple because they have mentioned that this is regular partition. If that is regular partition, everyone knows that delta xk for all k is what? Is the total length, 3 minus 2, divided by n, which is 1 over n. Yes? Okay, and then the point is I want to find m sub k. M sub k, in this case, because the function is continuous, forget about the word infimum and just work with minimum. Okay, I want to find m sub k. M sub k means the minimum of my function on the kth interval. Do you remember what was the kth interval? So let me put some dots here and some dots after that. Xk is, the kth interval starts from xk minus 1 and it goes up to xk. That was the kth interval. So let us limit ourselves here. So just concentrate on the kth interval, because whatever you say for the kth interval, you will see it works for all intervals, because the function is behaving the same way for all the intervals. Okay, now can you tell me what is m sub k? M sub k is the minimum of my function when I limit myself on this interval. Can you tell me what is mk? In this picture it is very clear. What is mk? Is this length. Do you agree? This is mk. But how can I find that length? It is my function calculated at x sub k minus 1. Do you agree?
Yes.
Okay, but my function is clear. My function is 3 times the input. The input is x sub k minus 1, so the answer will be 3 times x sub k minus 1. Yes? Do you remember I wrote a formula there up there for you for the regular partitions? So if I want to find x sub k, this is the formula. A is the initial point, B is the final point, N is the number of nodes, and this k is this index. But here in this problem, I don't want xk, I want xk minus 1. So everywhere in this formula that I have k, I replace it with k minus 1. So this becomes 3. Look at the formula, a. What is a in this problem? 2, at the starting point, plus, instead of k, I write k minus 1, and then I multiply it by b minus a over n, which I already did, and it is 1 over n. Do you agree? And then let me multiply this. So finally, this becomes 6, and this becomes 3 over n, multiplied by k minus 1. So this is my m sub k. Okay, so let us continue the calculation now. So I have m sub k, I have delta xk, and my question mark is about this. So I put these expressions back. So this means that Lpn is equal to sigma, k goes from 1 to n. Instead of m sub k, I put that expression. And then multiplied by delta x sub k, which is always fixed number. That's 1 over. Yes? Then the point is that we have to calculate this sum. And this sum is not very complicated. First of all, this 1 over n, can I pull it out from my sigma? Because this is a constant. The sigma counter is k, and it has nothing to do with k. So it always appears in every term of the sigma, so I can pull it out. Okay? And I am left with this term. And might be you are not very comfortable in working with sigma. Let me open it up for you. So how should I open it up? I have to put k equals to 1, I have to put k equals to 2, and then add all the terms up to the nth term. So if I put k equals to 1, it becomes this number 0. Yes? If I put 2, n times 1. If I put 3, it becomes times 2. Yes? And then I have to continue this list. If you are comfortable with working sigmas, work with that. But I just want to make sure that you understand what is the count. So this is 6 plus 3 over n. What is the last term? Can you tell me to see if you are understanding or not?
K minus n.
Yes, instead of k I put n, but it becomes n minus 1. And then this. Yes? Okay, but let us try to pack this up a little bit. So 6 appears here, appears here, appears here, appears here. So how many 6's are involved? N. So I'm adding them. So let me copy and paste this 1 over n, and let me write 6n instead of adding 6n times. It becomes 6n. But then you see that I have 3 over n here, 3 over n here, 3 over n here, 3 over n here. So I factor 3 over n out. From here, 0 is left. From the next one, 1 is left. From the next one, 2 is left. And from the last one, n minus 1 is left.
How did you get 6n?
What?
6n.
6 plus another 6 is 2 6.
Okay,
So it's
okay.
n times, yes? And then I have this closed. Is that clear? But there is a formula. This is a arithmetic progression. hopefully you have this formula in mind, I know that this sum is n times n minus 1 divided by 2. And I have written in the notes which formulas you need to know. This is one of them, okay? So then what happens, this becomes equal to, this n cancel that n, so this becomes 1 over n, 6n, plus, I have 3, a 2 down there, n's are cancelled, n minus 1. Agree? I hope that I haven't missed anything. So I multiply this in now, so it becomes 6 plus 3 over 2, n minus 1 over n. So if I haven't done any mistakes, hopefully, this is LPO. Is that understandable? It is a little bit long, but it is very elementary, it's not very complicated. The only thing that you need to note from your memory is this sum. Yes, and that's a very, very famous sum in mathematics. Yes, you have seen it in high school. Do you agree that this is LPO? But there is a second part of the problem. The second part is telling you that, okay, what is that limit? As I told you, why people are interested in taking limits? Because they are getting closer and closer to that area. Okay, so let us calculate this limit. But I think you can immediately calculate that. So what is this limit now? So do you remember we learned about, if I want to calculate this limit, I factor n out, I divide everything by n, so it becomes 1 minus 1 over n divided by 1. Or I can just simply write it as 1 minus 1 over n. And I am sending n to infinity. So what happens? This limit becomes 1. So this limit becomes 1, so the answer will be nothing except this one. And if you take this one, it's 15 over 2. So that's this limit. Okay, but I just want to tell you immediately something, that one thing is very clear. Do you see any notion of the derivative in this calculation?
No.
So that was the genius of Newton, who discovered there is a very nice connection between this calculation and the notion of derivative. For example, in this problem, you have seen it in high school. That function 3x, so I'm just counting on you that you remember something. Let us calculate the integral of that 3x dx from 2 to 3. If you don't know it, don't worry about it. But I hope that you can calculate this integral at this level. So what is the answer? You need to find, if you remember the Newton's law that I want to describe, you ask yourself, what is a primitive function for 3x? We learned this yesterday. So you should be able to answer this without limits. What was the answer? It is 3x squared over 2. Now Newton realized that put the upper limit here, so 9 times 3 is 27 divided by 2. Put the lower number here, 12 over 2, and subtract them. It becomes 15 over 2. So all this calculation will turn out to this, by genius of Newton, of course. And then you see that why we were interested in doing that game yesterday to find primitive functions, because he realized that if you want to do this calculation, you can do it so simple, but the price you have to pay is to play that game for your function. It means that you need to find the primitive function. So if you can't find the primitive function, then this calculation will be this much length. The length will be this much. So it is very, very good. And by the way, if I change the function to a complicated function, a little bit complicated, for example, if I make it 3 square root of x, then this method will fail. Can you see where it fails? I want you to feel. If I change the function, by the way, 3 square root of x is still not complicated function, but this immediately fails. Why? Everything you will have, instead of having k minus 1, you will have a square root of k minus 1, and then this sum will be square root of 1 plus the square root of 2 plus the square root of n minus 1, and there is no formula for it. I will be in trouble. But still, Newton's method works. Because if I ask you what is a primitive function for 3 square root of x, it's immediate. So this is not just as making things simpler. It's actually beyond that. It is making something which was impossible before possible now. Okay? So that's the idea of these ideas. But these kinds of calculation, it's part of your lesson, and you see that was exam question. So I just solved it to see that how this calculation goes. Any questions? So let's have a break. Yes?
Just to make sure that I understand correctly, in the square that we just calculated with the integral,
Yes.
the upper limit minus lower limit of the integral, right?
Yes, I will talk about that. But I just want to immediately tell you that why we were interested in the game of finding primitive functions, because genius of Newton makes this calculation through that simpler. But I will talk about that completely, okay? Yes, please. I'll not be able to prove everything here. The proofs are all in the book, but I will try to present it in a way that at least you understand the connections. But I also have some videos for my high school. I have put them there, so if you want to understand it deeper, you can see.